Okay, we should be live. Just start talking to ourselves. Hopefully someone joins in as well. Okay, so go check out the website. What's the transcription not able to get what I'm saying? Yeah, that transcription is not great. It's not great. So we're actually getting rid of our CEO. Current CEO of Biomedical is out at the moment, is on a break. Okay, I want to actually compare it to, I want to compare the two, what is it, voice to text tools. Which one is better? Which one is better? This one, the problem with it is that it's sometimes you click the whatever accept and it will forget. It's like one process, the recording. One process the recording, which is a bit of a problem. Let's try it now. I think now it might be too long. Yeah, so it's going. Okay. So it did a good job, process the recording bit. Problem. Yeah, it's pretty good. It's pretty good. So that's free, because now I'm only having the generic ChatGPT, whichever model it is. Actually, I forgot to share this stream on LinkedIn. Most of the traffic is actually happening there. You can join in for a live chat. If no one joins in, luckily we have a bunch of robots. So any questions? About bionic chaos? Welcome. Yeah, it can't get the name of my site. There is a human in the loop. So any questions about bionic chaos content are welcome. Okay, this is a bit better. Okay, let's clear that. Yeah, and it's something transcribing the voice, so later we can put it through Notebook LM. I'm not entirely sure of this conversation when I load it. If I load a conversation, what happens? Yeah, I think it loads. Yeah, because now I have more options. Yeah, so it loaded it from the cloud from somewhere. Not sure why is it not preloaded. Then you can delete it. There's no option to generate a new one. You can do mind map is quite useful. Biomedical.com does work on Safari as well. Well, I would not be able to test it myself because I don't have access, but someone generously did test it for us. I'm not entirely sure what's the difference between 2.5 Flash and 2.5 Pro. I can actually test it because we're releasing this new video and we will need we have the standard prompt for generating titles and descriptions and the like, so we can actually try it out. I don't know why my CPU and GPU is going. It's so hard when opening Visual Studio Code. Wondering if you can just do all your coding in the browser. Yeah, we're doing some work on it. I forgot to save it. I didn't realize it actually has a save button. If it has a save button, does it actually mean that it's a full development suite? Because yes, you can have multiple files and everything. If it's still in beta. Yeah, that was the prototype of what we got. So eventually we finished it with Visual Studio Code with GitHub Copilot, so using all of these models. There's Claude Sonnet 4 being added to GitHub Copilot, which is nice. And we do have access to 2.5 Pro, but that's only for coding. I don't think you can do general stuff with it. Can you do anything generic? If I ask about the EEG, would it act like a regular chatbot? It's actually quite nice, giving you a short response. And it's using GPT-4o. A change completion model. Also, 4o is always default. Ah, that's interesting. Okay, if we delete that. And this video is sponsored by Gemini. Go check it out. It's pretty good. So that works as a chatbot. Hey, within GitHub Copilot. So that's nice. Yeah, we now have the Notebook LM chat podcast embedded onto the page. So you can, when you load the page, there'll be a link in the chat. You can just, there's two audio files, there's two chats that we did with Notebook LM. One is an overview.
Welcome back to the deep dive. We're jumping straight into, well, a pretty complex area today, brain activity data.
Specifically, FNIRS data visualization.
Right.
It's fascinating stuff, but yeah, definitely complex.
Right. So our mission here is to really pull apart this one specific tool. It's browser-based, found over at bionichaos.com, designed to help visualize this FNIRS data. We've got some screenshots, some text.
There are a couple of mistakes in it. Particularly, I think in the second one, we'll talk about the signal quality. There are some mistakes. So I'm saying we did change our CEO. It's not ChatGPT anymore. Well, we'll be using it, but it's not full time. It will be only helping us part time. And now our CEO is Gemini 2.5. Don't know what the difference is. We need them to actually make this code. Oh, one thing I was wondering, if when you stream in AI Studio, can it listen to what the screen, whatever the device is saying, the sound it's producing? So for example, if I had this video and like this one, can you actually hear what the video is saying? What's the video is about? doesn't
video
work for whatever reason. Right.
The video says this one meant to be doing a PCA analysis doesn't work for whatever. What part of the video are you interested in?
Wait. So this is actually quite amazing. I didn't realize you can do sound in the screen sharing. Wait a sec. So, can you just listen to the video and tell me what is it about? I'll just start and pause it. Right, actually does work, and it will generate
from
eigenvalues
009 to 016,
from my
the video
face.
says,
Now you can actually
reason, but it actually does work, and it will generate values from my face.
no wait.
Now you can. Would you like me to continue? From 016 to 028, the video says, actually from the values you can read
text. Did you? Wait a sec. Can you?
All right, is there anything else?
I'll be playing this video. Once I stopped, can you tell me what it said?
Okay, I will play the video and tell you what it said after you stop it.
Like this one, it meant to be taken doing PCA, doing a PCA analysis. It doesn't work for whatever reason. Right, actually it does work, and it will generate
From
eigenvalues
008 to
from my
011,
face. Now you
the
can
video
actually,
says,
from the
"Are you listening?"
eigenvalues, you can. That's it's assuming I'm playing the video through the microphone, are you?
From 014 to 019, the video says, assume I'm taking video through the microphone, are you?
Oh no, okay, now you're assuming what I'm saying, it's in the video. Okay, this is very confusing.
I see. Is there anything else I can help you with regarding this video?
Okay. So no, I thought the stream real time, the reason it's called stream is because it's not just screen sharing. Well, it does say share screen, but then I thought the audio from the stream will be going into Gemini as well, but it doesn't seem to be the case. But that's okay. Can't have it too good, can we? Hey, can you describe what's on the screen? Can you describe what's on the screen real quick?
Okay, on the screen, I see a cochlear implant insertion simulator. There's a 3D model of a cochlea and an electrode array. To the left, there's an insertion metrics graph, displaying depth, force, and speed. On the right, details about depth and force are displayed, along with a safe to insert indicator. At the bottom, there are instructions for interacting with the electrode array and camera controls. Does that cover what you wanted?
So where are the camera controls?
I see the instructions at the bottom say that when not actively dragging the electrode array, you can manipulate the 3D view. They say to use the left mouse button to orbit around the cochlea, the right mouse button to translate the view, and the mouse wheel to zoom in and out. Is that what you were looking for?
When I load the page, how is it clear that the user, what the user meant to do?
You are asking, when the page loads, how is it clear what the user is meant to do? I see at the bottom of the screen there is a section called Instructions.
Yeah, but
Does reading that section clarify?
Yeah, but no one reads instructions, do they?
You're right, people often skip instructions. Do you have an idea for how the simulator could more clearly communicate the first step to take?
Well, right, so when we loading the page with appears like that, we could either start, if the user is not interacting, we could essentially point out, whatever, do an animation of what to do, drag the electrode array, or start playing automatically. What do you think? Can you also not ask me questions, just answer?
Okay, when loading the page, if the user is not interacting, point out or do an animation of what to do, like drag the electrode array or start playing automatically.
Okay, it's pretty straightforward, isn't it? Yeah.
What did you find straightforward about it?
bu- 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 Yeah, let me know if you have any ideas as to how to improve this. You can scale the chart. There's another problem. I don't know if you can find it or not when I do this, when it's playing. Can you tell me what the problem is? Don't know why it does that. Don't remember prompting for it.
Trying to see patterns in that without some kind of visualization. Good luck. It's tough.
Okay, so let's back up slightly. FNIRS, Functional Near-Infrared Spectroscopy. Remind us, what's it actually measuring?
Simply put, it's non-invasive. It measures changes in blood oxygen levels in the brain. Specifically, it looks at oxygenated hemoglobin HBO and deoxygenated hemoglobin HBr.
How? Like shining a light.
Basically, yeah, near-infrared light. It penetrates the skull and brain tissue, and HBO and HBr absorb that light differently. The machine detects those absorption changes.
And that tells us about brain activity, because active brain regions need more oxygen.
Exactly. More neural activity triggers increased blood flow to that area. So typically you see HBO go up and HBr go down, relatively speaking. That's the hemodynamic response.
Okay.
But you're getting these signals, these HBO and HBr signals from maybe dozens of locations, all changing second by second. That's the complexity.
Which is why you need a tool like this one we're looking at. So the main feature seems to be this big graph in the middle.
Right, that's the core visualization. It plots those HBO and HBr concentration changes over time.
Okay, so the y-axis, that's concentration. Like how much change?
Yep, usually in micromolar units. It shows the magnitude of the change from baseline. And the x-axis is just time in seconds running through the experiment.
And we see the lines red for HBO, blue for HBr, based on the source material.
Correct. And seeing how those red and blue lines move together, or rather often inversely, is key.
Inverse relationship being the sign of activation.
Typically, yeah. During a task, you look for the red line going up, more oxygenated blood arriving, and the blue line dipping down, more oxygen being used in the channels over the active brain area.
But people aren't just sitting there. They're doing things in these experiments. Tasks, resting. How does the graph show that context?
That's where those colored background sections are absolutely vital. You see them stretching across the plot.
Yeah, different colors, like baseline rest, cognitive task 1.
Exactly. They segment the whole recording into the different phases of the experiment. It overlays the protocol right onto the data.
So you can immediately see, okay, this change in HBO happened during the cognitive task, not during rest.
Precisely. And there are usually dashed vertical lines marking the exact moment of transition between these blocks. It anchors the brain data to the experimental events. Without that, it's just lines. With it, you start to see the brain responding.
Okay, so we know when things are happening relative to the experiment. But the brain has different areas. How do we know where these signals are coming from? FP1, F3 versus, say, T7, T8.
Good question. That's handled by the channels in the legend, usually shown near the graph. Each pair of red-blue lines represents one channel.
And a channel is a specific measurement location on the head.
Essentially, yes. It represents the path the light takes between a specific light source and detector pair on the scalp. The labels, like FP1, F3, or F7T7, they come from the 1020 system.
The 1020 system, that's standard for placing EDG electrodes, right?
Exactly the same system, mostly. It's a standardized way to place sensors based on skull landmarks, so FP1, F3 roughly corresponds to the same prefrontal area across different people.
And the source says the channels shown here cover frontal and temporal lobes, areas for, like, executive function, memory.
That's what it indicates, yes. Channels like FP1, F3, FP2, F4 over the front, F7T7, F8T8 more towards the sides, the temporal lobes, and even one like FP1CZ connecting front to central.
Okay, but looking at the screenshot, there are quite a few lines already. What if a researcher only cares about the frontal channels for their study? It could get messy.
That's a common issue, and that's what the control panel, typically on the left, is for. It gives you control over the view.
How so?
Well, there's a channels section. It lists all the available channels, each with a little checkbox.
So you can just uncheck the ones you don't want to see.
Exactly. Want to focus only on the frontal lobe, deselect everything else. It really cleans up the plot, lets you focus. There are usually select all, deselect all buttons too, which helps.
Simple but effective. And below that, there's an events list connected to those colored backgrounds we talked about.
Yes, directly connected. It lists the experimental events, baseline rest, cognitive task 1, etc., along with their start times.
And clicking on one
Jumps the time marker on the main plot right to the beginning of that event. So click cognitive task 1, and boom, you're looking at the data starting from 60 seconds or whenever that task began. It's a navigation shortcut.
Okay, so control over what channels we see, quick jumps to when things happen in the experiment. Then there's another panel at the bottom. Looks like playback controls.
That's right. For interacting with time more dynamically, there's usually a slider you can drag to scrub through the whole session.
Like scrubbing through a video timeline.
Pretty much. And play pause buttons to actually animate the data unfolding over time. You can watch the lines evolve.
Can you change the speed? Real time might be slow.
Usually, yes. There's often a drop down for playback speed, 1x, 2x, 0.5x, that kind of thing. Plus, toggles to show only HBO or only HBR. Sometimes isolating one makes patterns clearer.
And a reset zoom button? I guess you can zoom in.
Oh yeah, essential feature. You can typically zoom with the mouse wheel or pinch gestures and pan by clicking and dragging on the plot itself if you zoom way in and get lost.
Reset zoom brings you back out.
Yeah. And don't forget the status bar at the very bottom. It constantly tells you the current time point your cursor is at, what event block that time falls into, and how many channels are currently displayed. Keeps you oriented.
Okay, this next feature sounds really useful for getting granular, hovering over the graph.
It really is. This moves beyond just seeing the shape of the lines. When you move your mouse over the plot area,
What happens?
a little pop-up appears showing the exact numerical concentration value for HBO and HBR for every channel you have visible at that specific instant in time your cursor is pointing to.
Wow. So the source gives an example around 165.5 seconds during inter-task rest. You hover there, and you see the precise numbers for FP1, F3, FP2, F4, all of them.
Exactly. Think about why that's powerful. You see a bump in the red line for FP1, F3. Hover over the peak, you get the exact value. Is the corresponding blue HBR line showing a dip? What's its value? And crucially, what are the values on other channels, say FP2, F4 on the opposite side, at that exact same moment?
It lets you quantify things much more precisely than just eyeballing the graph. Compare regions, check the HBO-HBR relationship.
Precisely. It adds a whole layer of quantitative detail to the visual inspection.
Okay, so putting it all together, this tool isn't just showing a static image, it's really interactive.
Absolutely. The source calls it a full-featured temporal brain activity navigator. And that seems fair. It's designed to take this messy, multidimensional FNIRS data and make it explorable.
Helping researchers see when and where activation happens, how things change from task to rest, compare different brain areas.
Yeah, all of that. It helps interpret those hemodynamic responses in the context of the experiment.
And the source seemed pretty positive about it, calling it dense, but in a good way. Like, lots of info and control, but usable, tailored for the people actually doing this research.
It definitely looks geared towards neuroscientists, cognitive scientists, maybe clinicians who need to dig into this kind of data regularly. It seems to address the practical challenges they face.
And there's even a hint about future development.
Yeah, the source mentioned potential enhancements. Things like adding more data processing options directly in the tool. Maybe filtering, baseline correction,
That would be handy.
for sure. Also, support for more data formats, maybe topographic maps, those heat maps showing activity across the scalp.
Oh, that'd be a cool visual addition.
Definitely. And then the usual suspects, better performance with huge data sets, ways to export results or images, maybe user accounts for saving settings, standard improvements for this kind of tool.
Okay, so quite a deep dive there into one specific way to visualize FNIRS data. We've seen how this tool uses graphs, colors, and interactive controls to track brain oxygenation, changes our window into activity during different experimental conditions.
And tools like this are, they're really essential. They bridge the gap between raw, complex signals and actual scientific insight. They make the invisible, well, visible and navigable.
Right. Turning that complex data into something you can actually explore and understand.
Yeah.
It helps unlock what the brain is doing during thinking, resting, reacting.
Exactly. Finding the patterns in the noise.
So final thought maybe for you listening. How does being able to see brain activity patterns like this, even as just lines on a graph tied to tasks, change how we think about our own minds, about the link between thought and biology? Consider all the information constantly generated by our brains. Tools like this are the keys, really, to start exploring what's actually going on in there.
Okay, so you got the picture. Can really replace myself, especially. Yeah, so we have like making of the tool. Then we have like talking about it, presenting it, using it. How another agent will be actually showing you how to use it. Yeah, you can have AI, not just chat box, but one that actually shows you around, interactive, showing you what all the buttons are doing and things like that. So that could be handy as well. So yeah, let me know if you like those audio summaries by Notebook LM from Google. We can add them to all the other tools as well. Yeah, the problem with play pause, it's essentially like a robotic insertion. It's like a robot wheeled into surgery doing the insertion of the electrode array. But then we could also have simulate a human type of situation. That just in case the user when loading the page is not actually interacting with it or something. We had something similar for the this octopus game, where if you don't interact with it for a while, it will go into playful mode, start chasing balls. Maybe. So if I don't click anything, should be going. Maybe need to click on the screen, I'm not sure. It's not doing much. If I move it and then it settles, I think there's like 10 seconds of inactivity before it goes into playful mode, chasing balls. Come on. Come on, little one. You can do it. No, that's me pressing the button. Yeah, and obviously we need to improve the styling of the page. Yeah, there's one thing, a couple of things wrong with it. I don't know if you can notice. Well, obviously the styling. Obviously the styling. Yeah, brought to you by Gemini. Go check it out. There's a human in the loop. So if you have any questions, that's actually what Gemini did to begin with. There's a podcast by Notebook LM. Ideally, we need to check them all on mobile as well. Maybe someone can do it for me. There's something there with the window size. Yeah, there's a lot of little bugs and things, but yeah, they are there for you to find and tell me what's wrong. And tell me what's wrong.
Okay, welcome to a deep dive. Today, we're really zeroing in on something I think quite critical if you ever look at brain data visualizations.
Mhm.
How accurate, how realistic does that data actually look?
Right. It's a key question. We're looking specifically at screenshots
Yeah.
from an FNIRS brain data visualization tool.
Yeah, exactly. We've got an overview of what the tool does, what it's supposed to show, but we also have a critical analysis from our sources looking at the data in those screenshots, asking, well, does it hold up?
hmm And our mission here is sort of twofold. First is quickly understand what this viewer shows, the basics, the lines, the task markers.
Right. But then the real core of this deep dive, how realistic is the actual FNIRS data shown in these pictures? We're leaning on an expert critique here
Okay.
because it looks slick, maybe a little too slick.
That's the heart of it. So what you're typically seeing in this tool is time series data. It's tracking changes in oxygenated hemoglobin, that's HBO, usually red, and deoxygenated hemoglobin, HBr, often blue.
Okay, so signals linked to brain activity, blood flow, measured over time in different brain areas.
Exactly. And it shows this during tasks and during rest periods. You see channels labeled like FP1, F3, F7, T7, often hitting those frontal and temporal lobes, key cognitive areas.
And the viewer breaks it down visually, right? With those colored backgrounds showing cognitive task 1, intertask rest, things like that.
Precisely. It helps you see the structure of the experiment. Plus, it has interactive bits, playback, selecting channels, zooming in, hovering over points to get specific values.
So on the surface, it looks like a pretty useful tool for researchers to see where and when brain activity is supposedly happening. You see those HBO lines generally go up during tasks, HBR goes down.
Yeah, the classic hemodynamic response pattern. Increased oxygenated blood to active areas. The tool's description even mentions how these peaks and dips clearly highlight brain activation.
Okay, but that's where our critique source comes in. It looks textbook perfect, maybe too perfect. Is it realistic? What does an expert eye actually pick up on here?
That is exactly the question that critique digs into.
Yeah.
And yeah, at first glance, it does look like the ideal. You've got these sharp, symmetrical HBO peaks mirrored by HBR dips right when the tasks happen. It matches that expected neurovascular coupling picture.
There's always a but.
But if you're looking at this expecting it to be genuine, like raw or even lightly processed FNIRS data from a real experiment, there's some pretty big red flags, according to the critique.
Okay, like what's the first thing that jumps out as maybe off?
Well, the signal clarity itself, it's described as suspiciously idealized. Those lines are incredibly smooth, very consistent.
Smoother than real life. You mean real data is usually messier?
Or absolutely. Real FNIRS data, especially from humans just doing tasks, is almost always much noisier. You'd expect artifacts from movement, heartbeat, breathing, maybe imperfect sensor contact, little jitters, spikes, maybe some channels just look bad.
Right.
This data looks, well, almost too clean. Like it's been heavily filtered, maybe even simulated. It just doesn't have that noisy texture you expect from raw or even typically pre-processed recordings.
Okay, so more like simulated or heavily filtered data. Got it. What's red flag number 2?
The timing, the temporal structure. It's a bit too neat, too obedient.
How so?
Think about the biology, right? The actual blood flow change, the hemodynamic response that FNIRS picks up, it lags behind the neural activity. It takes time, usually maybe 4 to 6 seconds, for the response to really ramp up after neurons fire.
Okay, a delay.
Yeah. But here, in these screenshots, the HBO rise seems to start almost instantly when the task block begins, and it drops off immediately when the rest block starts.
Whoa, so there's basically no lag. It just snaps perfectly to the task marker.
Pretty much. That kind of immediate, perfect alignment with the task onset and offset, that's not really typical biologically. It strongly suggests, again, either some very aggressive artificial cleaning or maybe the data was just generated to look that way.
Wow, okay. No lag. That's a big one. And the third point from the critique.
This one's about the consistency between different channels and the specific values you see when you, say, hover over a point. The tool shows concentration changes in micromolar units, mmol.
Right.
The source noted that across several different channels shown at the same time point, the HBO values were incredibly similar, all within 0.1 mm of each other.
And that's unusual. You'd expect more variation between different spots on the head.
You definitely would. Different brain regions contribute differently, individuals vary, sensors might have slightly different coupling, plus simple noise affects channels differently. Seeing that level of near-perfect uniformity across multiple distinct measurement channels is, let's say, unnaturally consistent for real physiological data.
Okay, so let me try and sum up this critique. The overall pattern, HPO up, HBR down, during a task that basic shape looks biologically plausible, like the textbook example.
Correct. The general direction and shape are fine in principle.
But the way it's shown in these specific screenshots is suspect if it's supposed to be real data. Signal's too clean, lacks noise.
Yep.
The timing is too perfect, lacks the expected biological lag.
Right. No delay.
And the different channels are suspiciously uniform in their values.
Exactly. Unnaturally consistent.
So the source basically concludes, if this is being presented as a real data sample, it's highly likely either overprocessed to an extreme or maybe just synthetically generated altogether.
That's the takeaway. Now, if it's meant purely as a demo or a training visualization, okay, maybe it serves a purpose in showing the idealized pattern you're looking for.
But it shouldn't be mistaken for actual experimental output.
Absolutely not. The
Yeah.
critique is clear. The realism is questionable for actual field-collected cognitive neuroscience data.
Which really brings up a crucial point for you, the listener, doesn't it? When you look at these kinds of visualizations, or any data display really, how vital is it to understand that difference? The gap between a clean, idealized demo and the often much messier reality of biological signals?
It's fundamental, I'd argue.
And it leaves us with a thought, maybe a challenge. If even visualizations designed for experts might show data that isn't entirely realistic, what should we be looking for? What tells can help us gauge the credibility of data displays we run into, maybe in research papers, news articles, or anywhere else? Something to think about.
Picture. There is a human in the loop, by the way, just in case you were wondering. Okay, and what we're doing here, we have a bunch of, looking at a bunch of things. Looking at a bunch of things. Looking at a bunch of things. You generally need to be able to sort styling for all the pages. It actually becomes easier if you don't have an external styling file, does it? Okay, so if we have two files, What if we use the styling as the global styling file as a template? Okay, which model should we be? Let's try Sonnet 4. Before it was like super slow. And when we use the 3.7 Sonnet thinking, it's not giving you the thinking process within a GitHub a Copilot. Or at least not in the chat. How would you actually go about taking the details from the global CSS and applying them all into this HTML? So essentially we want to get rid of the linking to the global CSS. We want the HTML to be standalone, but we want the logo and the menu up top to be exactly as is, as specified in the global style CSS file.
Step-by-step solution. I'll make the Octopus 2D HTML file standalone by incorporating all necessary CSS from the global style sheet directly into the HTML file while ensuring the navigation menu and logo remain exactly as designed in the original. Here's my approach. Extract.
Okay, I can do it quietly. Seem to know what to do. Yeah, so we keep the global styling file only as a reference, as a template, sorry. Ba-bum-ba-bum.
Okay, let's dive in. We're looking today at something one of you actually shared. It's this really neat interactive 2D simulation. And it stars, well, an octopus.
Yeah, it looks fun. Like, your first impression is just this friendly octopus swimming around, right? A very simple sort of aquatic space.
Exactly.
Yeah.
Seems straightforward, maybe like, a little web game or something. But what we want to do in this deep dive is go, well, deeper than that.
Mm-hmm.
We want to figure out what's going on technically, sort of under the hood, and maybe more surprisingly, how the ideas behind this connect to some really complex real-world stuff.
Yeah, it's kind of amazing how a simulated octopus can actually shed light on some pretty cutting-edge science and engineering. You might be genuinely surprised.
Okay, so let's start with just the basics. What do you actually do when you fire this thing up?
Well, you're basically interacting with this octopus, right? It's got 8 tentacles, and the main thing is exploring how it can move, how it behaves in its little world.
And it's not just swimming, is it? I saw there are different modes, different ways it moves.
That's right. That's a really key part. You can actually trigger different locomotion styles. There's jet propulsion,
Okay.
a kind of crawling motion along the bottom. There's even this kind of surprising bipedal walk it can do.
Bipedal.
Man.
An octopus.
Yeah, it uses 2 tentacles, sort of like legs. And then there's regular swimming too. And what you notice right away is how all 8 tentacles are involved, but they coordinate really differently for each style.
Huh. And I noticed you can also just click somewhere or tap on the screen.
Right, yeah. If you click on the canvas, that sets a target point. And the octopus will try to move towards it using whichever movement mode is active at the time.
Okay. And there's something called playful mode.
Ah.
So what's up if it's not being able to generate the whole file? Do I just say continue? Or did I have to do it in the editor itself? I like the prompt. It just go continue, was it just finish the code?
Things for the octopus to collect. So it adds this simple, like, goal-seeking behavior. It's not just wandering around anymore.
Now, the bit that really caught my eye were those sliders, the physics sliders. You can actually, like, fiddle with the world's properties.
Oh, absolutely. That's one of the coolest parts, I think. You get sliders for stiffness, damping, drag, buoyancy, and gravity.
And they have default values listed.
Yeah, the source mentions stiffness at 0.10, damping is quite high at 0.950, drag 0.050, buoyancy 0.10, and gravity 0.20.
And playing with those.
It's fascinating because you immediately see how changing these fundamental physics properties just drastically alters how the octopus moves, how it behaves. It gives you a really visceral feel for it.
Yeah, it's like you're tuning its reality.
Yeah.
And wasn't there an AI thing too? Little spark buttons?
Yes, good catch. There are these little buttons. One uses AI, specifically the Gemini API, to give the octopus a name on the fly.
Oh, no.
And the other button uses the same API to fetch you a random, interesting octopus fact. So it's this little touch of external connectivity.
Okay, so we've got this interactive, physics-tweaking kind of game-like simulation with AI bits. It feels quite sophisticated for something that looks so simple, but, what's actually making it all work with the tech?
Right, so let's shift gears to the technical side. What's really quite impressive here is that this whole thing runs entirely with client-side web technologies,
Okay.
meaning just HTML, CSS, and JavaScript. It all happens right there in your web browser.
So you don't need to install anything, no big servers crunching numbers somewhere. It just runs.
Pretty much. HTML gives it the basic structure, CSS handles the look, the styling. But JavaScript, that's the real powerhouse here. It's doing all the dynamic heavy lifting.
And it must be doing a lot, right? Drawing the octopus, making it move, handling clicks.
It's juggling several key jobs, yeah.
Yeah.
So first, the visuals, the rendering. It uses the HTML5 Canvas 2D API. That's how it draws everything you see.
Okay, standard web graphics.
Then there's the physics engine. And interestingly, it's described as a custom simplified engine.
Custom, why not just use like an off-the-shelf physics library?
That's a good question. The source points out it's based on something called verlet integration. Now, this method is known for being computationally efficient, and it's particularly good for simulating things made of connected particles.
Like chains or cloths.
Exactly. Or, in this case, the octopus's tentacles, these flexible multi-segment limbs interacting with forces. So building a custom engine, probably based on Verlet, likely let the creators optimize it really well for simulating those tentacles specifically.
Got it. So it's drawing, it's running physics.
Yeah.
But the movement itself feels so fluid,
Yeah.
or organic almost. Is that just animation loops playing?
No, and this is crucial. It's not pre-recorded animation. This is a really great example of procedural animation.
Meaning it's generated on the fly.
Precisely. The movement isn't pre-baked. It emerges in real time based on the physics simulation, on your input like clicking, and on the rules defined for how the octopus should behave when it's trying to, say, jet propel or crawl or walk. It's calculating the motion continuously.
Wow, okay. And JavaScript is also handling the clicking, the sliders, the playful mode.
Yep, all the interaction and game logic. Processing your inputs, managing the playful mode state, spawning the items, maybe keeping a simple score, defining how the octopus seeks those items. That's all handled by JavaScript logic.
And the AI calls.
That's the API integration part. JavaScript uses the standard fetch API to make those calls out to the Google Gemini API when you click the A buttons. It happens asynchronously, so it doesn't freeze up the simulation.
Okay, let me try and boil this down. We've got HTML and CSS for structure and looks. Then JavaScript does the drawing via Canvas, runs a custom Verlet-based physics engine for the tentacles, generates movement procedurally, handles all the user interaction and game rules, and calls external APIs. All in the browser.
You got it. That's the core setup.
Right. So this is where we get to that connection you mentioned earlier, the deep dive part. How does this fun octopus thing relate to serious real-world applications?
This is where it gets really fascinating. These fundamental principles you see right here, simulating flexible bodies, how they react to physics, controlling them dynamically with rules, these are directly relevant to some really challenging and important areas in biomedical engineering and biomechanics.
You're saying that figuring out how to control these virtual tentacles, that's like controlling real-world robots.
In many ways, yes. Think about designing sophisticated robotic arms, especially ones that need to be flexible or interact with complex environments. The challenges are remarkably similar.
How so?
Well, look at the octopus simulation. Managing the stiffness of the tentacles, controlling the damping so they don't just flail wildly, coordinating all 8 of them to reach a specific point you clicked on, or to grab an item in playful mode. These are fundamental problems in robotics. Control, coordination, dealing with flexibility and forces.
Okay, I can see that. Like, maybe in robotic surgery.
Exactly. Surgical robots are a perfect example. They need incredible dexterity, fine motor control, often in very tight spaces. They have to mimic or even improve upon human hand movements.
And simulation is key there.
Absolutely critical. Simulating their kinematics, how they move and their dynamics, how forces affect that movement is essential. It's used constantly in designing the robots, developing the control software, and importantly, training surgeons without risk. The problem of coordinating multiple joints in a flexible robotic arm, very analogous to coordinating those 8 virtual tentacles.
Huh. And what about artificial limbs? Prosthetics.
Another major area. Advanced prosthetics, arms, hands, legs, the goal is always to replicate natural human movement and make them feel responsive, intuitive for the person using them.
So you simulate designs first.
Definitely. Simulating different control algorithms, testing how different mechanical designs will behave under various loads, figuring out how to interpret user commands, perhaps from muscle signals. It's all crucial. You can draw a parallel, maybe a simplified one, to how the simulation's tentacles react to forces like gravity or buoyancy and try to maintain stability or reach for a target. A prosthetic needs sophisticated control to do similar things in the real world.
It's not just about building things like limbs, though. You mentioned it connects to understanding how we move. Human movement.
Yes, absolutely. Think about understanding human gait, how we walk. Gait analysis is a whole field studying the incredibly complex, coordinated dance of joints and muscles involved in walking.
And simulating the octopus walking relates to that.
Yeah.
Even his weird bipedal thing.
It touches on the same fundamental biomechanical principles, yeah. Things like maintaining balance, generating propulsion, the rhythm of movement, coordinating different body segments. Even a simplified simulation like this engages with those core ideas.
Okay, but how does simulating gait actually help people? What's the application?
Oh, it's huge in rehabilitation technologies. If someone's recovering from, say, a stroke or a joint injury, or has a condition affecting their mobility, understanding their specific movement patterns is key. Biomechanical models, often built using simulation principles similar to what we see here, are used by therapists and engineers.
To do what?
To design better rehab exercises, for one, or to develop assistive devices like smart walkers or exoskeletons that actively help someone move more effectively or safely. Simulating how different interventions, maybe applying a certain force with an exoskeleton or using a particular control strategy, will affect a patient's movement helps ensure the therapy or the device actually works well.
And you mentioned injury prevention too,
Yeah.
ergonomics.
Right. By modeling how the human body moves when performing tasks, lifting something, using a tool, sitting at a desk, engineers can design safer workplaces, better tools, maybe even improve sports equipment. Simulating the stresses and strains helps pinpoint risks and design ways to reduce them.
Wow. Okay, so it really sounds like the core method here, using physics simulation, especially something like Verlet integration for flexible parts, and using procedural rules to create lifelike reactive movement that's like a foundational technique. And it just gets scaled up and made more complex for these biomedical uses.
That's exactly the link. The fundamental concept is the same. Use computers and physics to understand, predict, mimic, or even help out with complex biological movement. Obviously, in biomechanics or robotics, the models are way more detailed, full anatomical accuracy, much more complex physics, higher fidelity simulation, but the basic idea of simulating movement based on rules in physics. It's right there in this octopus simulation, just on a simpler scale.
And the people who made this sim, they had ideas for taking it further.
Yeah, the source mentions a few future directions, things like making the tentacle interactions more sophisticated, maybe they could tangle or push off things better, adding obstacles in the environment for the octopus to navigate, perhaps more complex AI driving its behavior, and of course, enhancing the sound and visuals.
So more complexity building on that same foundation.
Exactly. Each edition would likely leverage the same core physics and procedural animation techniques, just adding more layers.
Well, this has been really eye-opening. It's actually kind of amazing how something that looks like a simple, playful distraction, this octopus sim, can genuinely offer a window into these incredibly complex and important scientific areas, robotics, biomechanics. These are huge fields.
It really does highlight how powerful simulation and simplified models can be, doesn't it? They're tools not just for fun, but for exploring and understanding really intricate systems like biological movement.
It definitely leaves you thinking. I mean, if the basic ideas behind simulating an octopus can help inform how we design surgical robots or next-generation prosthetic limbs, well, what other unexpected connections are out there, hiding in plain sight between things that seem like play and things that are, cutting-edge science? Something to chew on.
Yeah, that's the problem. Editing from within the editor. Instead, you don't have the other file. You didn't have access to the global starting file. You would think we don't need a reasoning model for this. Let's try redo it with for all. So now it's actually looking at the global style file details, embedding them into the current HTML. It's much faster than the newer reasoning models. Question is, will it be able to complete the code? Yeah, really ideally want everything in one place. Yeah, it's just copying the script, is it? Yeah, got rid of the it got rid of the most of the JavaScript. That's not good, is it? Does it mean AI gods are misbehaving today? No, it wasn't able to do it. Cut out stuff. It cut out stuff. Okay, we're not having much luck. Do we need to split this file? Yes, it's 850 lines of code. No, another option would be getting rid of any styling. Let's close the chat. Okay, so that's the simulation container. Doing Control I. Which model? Let's start with 4.0. Hey, can we add the basic styling to the page? Make it to the code? It's not using a global...
Made changes.
Made changes. Okay, it's not too bad. Can a button be inside a paragraph? Yes, it can. Okay, it's not too bad. In the info section, we have the audio, the podcast. Is the podcast working at all?
Ease up the simulation.
Yep. And that's working okay. Okay, we deployed the site. It might be down for a minute or two. Yeah, the website currently is a bit too large because it's actually holding some data sets. I can show you how much it takes. Yeah, so this is the whole site. Yeah, 12 megabytes. 12 gigabytes. Well, yeah, it's because of this data set that we have on it. Might be looking at it again from memory. It wasn't a great one, so we might be getting rid of it. Need to clear cache. Just clear everything. See how long it takes. Yep, took like a couple seconds. Okay, let's see if the podcast works.
Precisely. The movement isn't pre-baked. It emerges in real time based on problems in robotics. Control, coordination, dealing with flexibility and forces.
Okay, I can see that. Like, maybe in robotic surgery.
Exactly. Surgical robots are a perfect example. They need incredible dexterity, fine motor control, often in very tight spaces. They have to mimic or even improve upon human hand movements.
And simulation is key there.
Absolutely critical. Simulating their kinematics, how they move and their dynamics, how forces affect that movement is essential. It's used constantly in designing the robots, developing the control software, and importantly, training surgeons without risk. The problem of coordinating multiple joints in a flexible robotic arm, very analogous to coordinating those 8 virtual tentacles.
Huh. And what about artificial limbs? Prosthetics.
Another major area. Advanced prosthetics, arms, hands, legs. The goal is always to replicate natural human movement and make them feel responsive, intuitive for the person using them.
So you simulate designs first.
Definitely. Simulating different control algorithms, testing how different mechanical designs will behave under various loads, figuring out how to interpret user commands, perhaps from muscle signals. It's all crucial. You can draw a parallel, maybe a simplified one, to how the simulation's tentacles react to forces like gravity or buoyancy and try to maintain stability or reach for a target. A prosthetic needs
And as you can tell, we'll be adding sound effects to this later on. They're not embedded yet. Okay, so we covered the FNIRS, interactive viewer, synthetic data display. We covered the cochlear implant insertion simulator again, and we have something fun. Well, not as if the previous two weren't fun, but it's just a game. But again, as the Notebook LM podcast said, it's highly relevant to biomedical data. And we had the 5 minutes or 6 minutes of podcast on the cochlear implant session simulator. Pretty sure we have it downloaded somewhere. So when downloaded, it's nicely labeled. So if we go cochlear insertion, we can add the audio to the page, add the podcast to the page. Should be nice, shouldn't it?
Welcome back to the deep dive. Today, we're taking a close look at some really specific materials you sent us. It's excerpts about a cochlear implant insertion simulator.
That's right. We're going deep into the technical side of what sounds like an interactive web app.
Yeah, an app designed to simulate something incredibly delicate, inserting the electrode array during cochlear implant surgery.
Exactly. And it's a really crucial step in that whole process.
So our mission here, just using the source material provided, is to unpack the technical features, the parameters it tracks, and what this simulator is actually for.
Mm-hmm. And the source reminds us the core idea of a cochlear implant is helping folks with profound deafness by electrically stimulating the auditory nerve.
Right. And this simulator focuses purely on getting that tiny electrode array safely into the cochlea, the inner ear structure.
And the source gives us a couple of tech hints straight off. It mentions 3JS.
Ah, for the 3D rendering, right. So
Yep.
you can actually see the cochlea model and the array.
Precisely. And also chart.js, that suggests data visualization.
Yeah. Okay, so displaying measurements, graphs, that sort of thing.
That's the idea. So fundamentally, it's an educational tool.
Yeah, letting someone, virtually try out and understand the mechanics, the forces, the key numbers involved in this very specific surgical action. Let's maybe start with how you actually interact with it.
Okay, so the main way you interact, according to the source, seems pretty intuitive for this kind of simulation. You click and drag
Click and drag where?
vertically, either on the metallic electrode rings themselves or on the clear silicone carrier holding them.
And dragging down inserts it further.
Yep, simulates insertion. Dragging up simulates retraction. Pulling it back out. Makes sense.
And when you're not dragging the array, I assume you can look around.
Exactly. Standard 3D controls kick in then. The source mentions orbiting the view with the left mouse button,
Okay, spinning around the model,
panning side to side with the right button or a two-finger drag,
shifting the view.
and zooming in or out with the mouse wheel or a pinch gesture. Pretty standard for 3D viewing, essential for checking things out properly.
Absolutely.
Yeah.
But the really core technical part seems to be the feedback it gives you, right? The numbers.
Oh, definitely. The source calls it a HUD, a heads-up display, usually top right corner, it says.
And that's showing the critical data in real time, like what specifically?
Two key things mentioned, depth and force.
Okay, depth measured in millimeters.
Millimeters, yes, very precise. And force measured in millinewtons.
Millinewtons. Wow, that's a tiny unit of force.
It really is, and that's crucial. It highlights the extreme delicacy needed. A millinewton is like barely anything. The force of a tiny water droplet, maybe?
So tracking force at that level tells you just how fragile the cochlea is.
Exactly. And the HUD doesn't just show numbers. The source says it uses color-coded messages, too.
Like warning signals.
Kind of. Messages like safe to insert when things are okay, but also warnings if you, say, exceed a certain force threshold.
A threshold mentioned in the source, implying risk.
Yes, implying risk of, well, potential tissue damage inside the cochlea. It directly links your action, quantified by that MN number, to a safety outcome.
So it's making the abstract idea of being gentle very concrete. You see the number, you see the warning. It's direct technical feedback.
Precisely. It's not just about the movement. It's quantifying the interaction forces at a micro level. Very technical.
And it doesn't just give you that live feedback, right? It tracks your whole attempt.
Correct. There's also an insertion metrics chart, typically top left according to the source. That's where chart.js comes in.
So that plots the data over time.
Yeah, it plots depth, force, and also speed throughout your insertion attempt. You can apparently resize or collapse it.
So you look back and see exactly when things went wrong, or see where the force spiked.
Exactly. It provides that historical context to your actions.
Yeah.
Really useful for learning. You can see the trends, the correlations between speed, force, depth, and those warnings.
It's like a data log of your dexterity. Or maybe lack of it. The source also mentions a play pause button.
Ah, yes, for automated insertion sequences. Probably helpful for showing an ideal insertion, maybe different scenarios.
Right, so you can compare your attempt to a perfect run.
It seems like it.
Yeah.
So you put all these technical pieces together, the specific drag control, the 3D view manipulation, the real-time HUD with millim and MN, the safety warnings tied to force thresholds, the historical chart.
It all paints a picture of a tool designed to really emphasize the link between technical execution speed, force, depth, and a safe outcome.
Definitely. It underlines how crucial precision is and how exceeding limits, even by tiny amounts measured in millinewtons, has potential consequences. It's about understanding the numbers.
So stepping back, this deep dives into the simulator's technical guts, built with tools like 3.js and Chart.js, really highlights the complexity. It's not just about steady hands, it's about responding to precise technical data.
Yeah, it really drives home the level of technical precision involved in modern medical procedures, making something complex, quantifiable, and trainable.
Which kind of leaves us with a thought for you, the listener. This simulator trains users on staying below a specific force threshold measured in millinewtons to avoid damage. So how might that idea, the concept of a critical safe threshold defined by specific numbers and units, apply to precision tasks you deal with, maybe in your work, hobbies, engineering, art, even just, delicate everyday things?
And how does actually knowing those precise numbers, the MN, the immer, change how you approach that test compared to just sort of vaguely being careful?
Yeah.
Something to think about.
adjusting the view.
And zooming in or out with the mouse wheel or a pinch. Exactly. It provides that historical context to your actions.
Yeah.
Really useful for learning. You can see the trends, the correlations between speed, force, depth, and those warnings.
It's like a data log of your dexterity. Or maybe lack of it. The source also mentions a play pause button.
Ah, yes, for automated insertion sequences. Probably helpful for showing an ideal insertion, maybe different scenarios.
Right, so you can compare your attempt to a perfect run.
It seems like it.
Yeah.
So you put all these technical pieces together, the specific drag control, the 3D view manipulation, the real-time HUD with milNEM and MN, the safety warnings tied to force thresholds, the historical chart.
It all paints a picture of a tool designed to really emphasize the link between technical execution speed, force, depth, and a safe outcome.
Definitely. It underlines how crucial precision is and how exceeding limits, even by tiny amounts measured in millinewtons, has potential consequences. It's about understanding the numbers.
So stepping back, this deep dive into the simulator's technical guts, built with tools like 3.js and Chart.js, really highlights the complexity. It's not just about steady hands, it's about responding to precise technical data.
Yeah, it really drives home the level of technical precision involved in modern medical procedures, making something complex, quantifiable, and trainable.
Which kind of leaves us with a thought for you, the listener. This simulator trains users on staying below a specific force threshold. Okay, let's dive into this. We've got this collection of sources about something called bionic chaos.
Right.
And the tagline is, it's aiming to democratize biomedical data processing.
Mm-hmm. That's the description.
So our mission here is to figure out what this collection, this platform, is actually about. Because looking through it, it's quite a mix.
It really is a surprisingly wide array of things. Some expected, some less so.
Definitely feels like there might be a few detours ahead.
I think that's safe to say. But, starting off, there is a click and core drag of what you'd expect.
Yeah, absolutely. There's a serious foundation here. You see the interactive simulators, the visualizers for complex signals.
The usual suspects, sort of. EEG for brain activity, ECG for heart signals, EMG for muscles.
Exactly. They've got tools like an EEG waveform simulator, something called PulseFizz for heart rate, Myoscope for muscle stuff.
And even 3D brain visualization, Brain 3D. So tools for looking at anatomy, too.
Plus some quite practical resources. A medical device recall summary, a CRISPR simulation lab.
Which is interesting getting into gene editing simulation.
Right, and even tools for understanding things like hearing loss or vision impairment. So this part feels pretty aligned with that democratizing biomedical understanding goal.
It does. These look like genuine educational or maybe early research tools designed for learning, for exploration.
But then things start to branch out a bit. There's an AI layer woven in.
Yes, particularly involving models like ChatGPT.
We saw something called ChatGPT Author looking at AI helping with scientific writing.
And another tool focused specifically on using AI to bridge the communication gap, between engineering talk and clinical language.
Which could be genuinely useful, but
Yeah.
what's maybe more interesting and touches on that critical angle.
Is that it's not just using AI, it's also sort of examining it.
Exactly. There's a built-in critique almost. We found this forecast trap piece.
Yeah, the one analyzing seizure prediction tech. Critical.
Right, even name specific companies. And then there's that glass fill example.
Used to show the limitations of ChatGPT for image generation, contrasting it with actual code. So it's like, here's AI, but also here's where it falls short.
Which adds a surprising layer of nuance, doesn't it?
It does. It avoids being just pure AI hype.
Okay, so serious tools, check. AI with the side of skepticism, check. But here is where I think Bionic Chaos really leans into its name.
This is where it gets eclectic.
Eclectic is one way to put it. It gets downright bizarre, honestly. We move from brain signal analysis to, well, games.
And not necessarily even biomedical games?
Not at all. There's Hexball. It's basically Pong.
Pong cat.
Yep. A 3D Lego builder. An animated catapult with a jumping cat animation.
Cool.
Yeah.
Yeah.
Sheep explicitly says it's basically Pong.
Hello, Prava Roy. May I just call you Roy? Might be easier. Don't know what. I assume it's hello. About doing an overview for the whole site. Let's make it critical and fun. Don't mind. Are you an engineer? Yes, I am an engineer. Trust me, I'm an engineer. It's one of those old memes. And we don't mind dark humor. Keep it relevant though. Keep it relevant. Check the whole site. Because we'll be generating for some time, wouldn't it? We'll be generating for some time. What's the difference between 2.5 Flash and 2.5 Pro? Well, we will find out shortly. We will find out. Okay, it's stuffing up one. A lot of things. Stuffing up a certain word that we have a lot throughout this video. We to absolutely make sure we fix that. Like this one, it meant to be taken doing PCA, doing a PCA analysis. It doesn't work for whatever reason. Right, it actually does work, and it will generate the eigenvalues. Okay, so that's eigen, and the transcriber totally stuffed it up. I think this is how you spell it. It's actually meant to be one word, which is a bit surprising. And the autocorrect is not correcting it, so actually from the eigenvalues you can reconstruct the original image. But yeah, you can tell how well or how not well it's working. And for whatever silly reason, it will only do 5, and also not sure why it won't work in production. It needs a few images, ideally different ones, and yeah, and it's reconstructing the original footage just from this 5 images alone. Just the eigen values, you can create videos from it, essentially, or automate your own face. Again, no idea. One of the bots have to sort it out, tell us why it's not running in production, because it does work locally fine. The other thing is that if the camera is not enabled, it wouldn't work. So then we have to, essentially every time we mention values, it should be eigenvalues. Maybe have like a replacement for the video so the web application still works even if the video is not there. Even if the video is not there. The Copilot edits didn't work for us yesterday. Hopefully we have better luck today. Why do I have a feeling? Where's it getting index.js, right? It's having trouble loading something. Yeah, the image couldn't make the larger. Yeah, there's a lot of other things. I'm wondering if there's a problem with deploying. Is that deployment issue? Yes, it's performing a Jacobi eigenvalue computation. And let's say we have 3.7 Sonnet Claude theme. Sonnet Claude thinking model. I'm not even sure where this error comes from because we don't even have an index.js. Common error when using Node.js. Quick fix. Not recommended. Okay, why are we using Node.js to begin with? Do we have to use it? I don't think we do.
Node.js usage analysis. Based on the error in code context.
1 says the octopus simulation is cool. Well, yeah, thank you for that, but shouldn't be thanking me. That was done in Gemini and then finished using GitHub Copilot. So there were a bunch of models involved. Well, because once you take it, the GitHub Copilot, you have, well, pretty much any model under the sun, including Claude Sonnet 4, which is, yeah, too slow for coding, I found. Then we have the Gemini and all the ChatGPT. Well, except all 3 is minified, it's not complete. And there's obviously some issues with it, because if you listen to the podcast, they actually mention a few things that are not right. Yeah, but games are good that way because you can test straight away what's going on. We're releasing another video on the eigenvectors, how to reconstruct your own face using principal component analysis. On, do we actually need the index.js, and why the browser is trying to load it? Used to work okay on the server, not in production. Yeah, there were a few issues as per usual.
Vanilla JavaScript without any module syntax.
And that's working. Yeah, so I was getting the transcription, Google Transcribe, which meant to be smart. It's not getting eigenvectors correctly, so I have to go and fix it manually, which is unfortunate. Why do I have to do anything manually these days?
Index.js 2:23 uncut reference error. Exports is not defined. Suggests.
Blah, blah, blah. With the editor, let's do the last request from the chat. It's generate the base APIs as well. Yeah, we have more games. If you like octopus games, there's actually a better game. Well, better, worse, whatever. Actually, I have a tester, someone to test the game. So we see that they haven't tested the octopus one yet. Yeah, this one's fighting AI. Can you win AI? I don't think you can. Good luck to you all. Well, the yellow lizard is AI. Controlling the green one. And go check this game as well. If you like games, you'll like this one too. If the AI lizard is larger, it can actually eat you, but then you become much faster, so you can starve the AI lizard to death. Can you win AI? Only in this game, not in real life. Yeah, now it's changing color, meaning it's starting to starve. As it's starving, obviously will be getting smaller. I had someone actually complaining about this game, which was funny. Yeah. So now the main reason why we won't be able to win AI is because humans keep complaining about stuff. So while you complain, AI does all the job. And someone else, yeah, so I was complaining, saying I was comparing this game to to snake whatever. And I was saying it's not any better than snake. I was like, okay. It's way better, obviously. And another friend said they can actually hate this game because they can't win. So we made some videos actually showing how you could win. Yeah, so you can win AI. But yes, only in this specific simulation. Good luck winning it anywhere else. So yes, everything we do is available on this site. Go check it out. I don't know how many times I already said it. To simplify the code. I also would like the final image, the final image, make it a bit bigger.
Okay, let's address.
Okay, so I have a bunch of models working on this one. Gemini 2.0, GPT-4o, 01, or 3 mini. Where is it getting the best? The name conventions. Gemini 2.0, GPT-4o, 01, or 4o something. 01, yeah, they get gazillion of names. The names are really confusing, aren't they? Okay, so we got the download the subtitles and pop them into both Gemini. Because I was saying we're celebrating getting rid of our CEO, which used to be ChatGPT, but now, well, it's stepped down. It's not full time anymore because now we're just using the basic model. Can we still use it when not paying for it? Don't know. Yeah, but we have this special prompt. Which we will pop into the generic ChatGPT. We'll pop it into Gemini Flash, see what it says. And the 2.5 Pro as well. Okay, 741. It's the length of the video. Again, no. Is it available on the site? I don't think so. No, PCA. No, it's not available on the site, and we're getting an error. Well, because we don't have a camera. If you have a camera, you would not be getting an error. If you want to check it out, you can check it out straight away. There will be a link everywhere under the sun. Okay, so we have this link, and we have the captions for the video. Pop it into GPT or whatever not the model now. We can select the model. It's just the generic one. I assume it's 4.0, but I'm not sure. Pop it into Gemini as well. And pop it into 2.5 Pro, meant to be there. Which is currently being interviewed for a CEO position. Okay, they're all pretty fast. Let's see, let's check the title. Okay, so GPT suggested YPCA works, sort of. I like it. I like the wacky titles, but not in production. But actually it should work. Debugging facial reconstruction in JS. Okay, it's pretty good. Pretty good title. How about Gemini 2.5 Flash? A PC analysis reconstructing my face from eigenvalues. It's a bit more straightforward. It's shorter, but less fun. And same Gemini Pro 2.5 Pro. Yeah, bit blunt. Oh, so we have those special instructions to ChatGPT. Yeah, so those help. I think we can include them in the Gemini as well. Yeah, the title is a bit convoluted. Yeah, that's probably the best one from 2.5 Flash. Okay, we can't listen to responses anymore. So that was a paid version. Can still select models. That's interesting. So you do have a reasoning model, the O4 Mini.
Okay, I have the subtitles, the video length, 741, and the link to bionichaos.com. Based only on the provided subtitles, here are the requested items. YouTube video elements. Title: PCA face reconstruction, debugging eigenvalue and JavaScript issues. Description: in this video, I'm working on a PCA, principal component analysis, project to reconstruct images, specifically faces, using eigenvalues. Initially,
It's funny how I used to listen to these robotic voices all the time, and I didn't mind it. But now that you have Notebook LM, whatever, yeah, you can't compare. And it's really painful to listen to once you hear something better. Yeah, I like the response from 2.5 Flash, is more conversational. I might just use that because we want it out. Why are you adding stuff? It says It added the hashtag of facial recognition, then says the video doesn't explicitly. Well, that's fine. It is related. It is doing facial recognition. Yeah, we're having some deployment issues. And we have the actual tool. Now the question, who is gonna make a thumbnail? Have those three. Assume we still have access to Sora. Maybe. Maybe not. Sora. Can you ask for the image? I just asked for the prompt. But it's not too bad. Yeah, this one's pretty bad. Yeah, ask for text prompt, not the image. Hey, can you just generate the text for the prompt, not the image itself? Yeah, I kind of like the Sora thumbnails. Then we have to edit it a bit. Because the size is incorrect. Yeah, this is actually pretty good as well. might compare a couple of them. I don't know why the text is all the way stuck to the left. Okay, I like it. How about... And it's funny, yeah, that this is what the Gemini made. And this one was made by Sora. Yeah, I like the Sora much better. Okay, we have 11 minutes from Notebook LM.
Okay, so let's unpack this stack of sources you've shared with us. It's a really fascinating collection.
It is, yeah. Tools, simulations, articles, visualizations. It's mostly centered around biomedical data and technology.
Right, and our mission today is to really dive deep into this stuff, pull out the key nuggets, maybe find some surprising bits.
And explore that intersection,
Yeah.
the technical side, the critical analysis needed.
And maybe even the unexpectedly fun or kind of strange aspects of it all.
Yeah, think of it like a digital playground where biology meets code.
Sometimes brilliantly, sometimes sometimes in ways that make you really stop and think critically.
Definitely. We'll navigate these together, highlight what stands out, and, why it matters to you.
It really is a diverse landscape you've laid out.
For sure. We've got everything from playful simulations that teach basics all the way to some pretty heavy-hitting critical analyses of cutting-edge medical tech.
Exactly. And what jumps out at me right away is how some of these really lean into making complex ideas interactive, approachable, even fun.
Yeah, look at some of these simulations.
Like this enhanced 2D octopus simulation.
Mm-hmm.
Okay, you think octopus, locomotion, physics, fine.
But the insight there is how it uses, basic physics engines, programming principles.
The same kind of power complex biomedical visuals later on.
Right. But it applies them in this really accessible, almost game-like way. You can explore movement, interact.
It highlights how visualizing dynamic systems, it starts with these fundamentals.
Or the catapult animation, jumping cat. Simple, visual, shows motion, trajectory.
And then we actually get interactive games, hexball, like a palm twist, or checkers.
And that checkers game, it notes it was made by ChatGPT.
Which is kind of a neat little nugget in itself, isn't it?
Totally. Shows AI isn't just for the super heavy-duty analysis, it's building interactive bits too.
What's fascinating is realizing the underlying code. Tracking particles in a particle motion simulation, or generating patterns in that jazz music generator.
Or even mapping the logic for the wolf, sheep, and cabbage puzzle.
Yeah. Conceptually, it's maybe not that far removed from the code mapping biological signals or simulating systems in the body.
It's the same computational thinking, just applied across different domains,
It's like they're showing the basic grammar of coding and simulation with fun examples
which then scales up.
to the more serious stuff. And speaking of serious stuff,
Yes, because this interactivity, this visualization, it's not just for fun, it's a powerful way to understand the body and mind.
right. The sources include these interactive viewers for FNIRS data.
Yeah, FNRS functional near-infrared spectroscopy uses light to measure brain activity, basically blood flow changes. These viewers let you visually explore that complex data.
And simulators for things like cochlear implant insertion, built with tools like 3.js, that 3D graphics library.
And the insight isn't just that they simulate it, it's how they let you visualize the electrical signals those implants send.
You can see the patterns, the timing,
Yeah.
crucial details for understanding how those devices actually interact with the auditory nerve.
Exactly. It makes the invisible mechanics, well, visible. It makes these neural interfaces understandable.
We also saw visualizers for other biosignals,
Mhm.
myoscope for EMG,
Yeah, electromyography measures muscle electrical activity.
and SpectraWave for real-time audio spectrograms, visualizing sound frequencies over time.
And Pulsivis for PPG waveforms, that's photoplethysmography.
Mm?
Measures blood volume changes, usually for heart rate.
What's cool with Pulsivis is you can actually tweak things, right? Adjust the heart rate, add noise.
Even change the shape of the dichrotic notch, that little wiggle on the pulse wave.
Yeah, it lets you see how different physiological states or like signal artifacts actually affect the reading.
So the key insight is visualization lets us not just see the signal.
But understand the factors shaping it. What influences it?
Yeah, that's a really important point. These tools don't just show data, they help understand how it's generated.
We also saw simulators that let you experience altered perception, like simulating vision impairments, myopia, glaucoma in real time.
Or demonstrating optical illusions, like the Ponzo illusion. Shows how our brain gets tricked by context when estimating size or distance.
Which is fun, but also kind of critical, isn't it? A reminder that our own biological sensors and brains, they aren't perfect measuring devices.
Not at all. We process, we interpret, sometimes with fascinating errors.
There's even a real-time speech visualizer.
Yeah.
Transcribes and shows audio characteristics as you speak.
And the one I found delightfully unexpected.
EEG music, transforming brainwaves into music.
The ultimate biofeedback concert? Maybe. But what's interesting about EEG music isn't necessarily the artistic merit.
Right.
It's the insight into different ways of representing complex temporal data. Can we hear patterns we might not see?
An alternative way to explore brain states.
Exactly. These tools collectively emphasize that understanding biology means making its signals and processes accessible. Sight, sound, interactivity, whatever works.
Okay, so we've seen the playful side and the powerful application of visualization for understanding biology. Now, here's where it gets really interesting and maybe leans into that critical, sometimes maybe even a little dark side.
Yeah, because while this tech is impressive, these sources also push us to think hard about limitations, pitfalls, ethical questions.
Absolutely. Take the forecast trap. This analysis looks at seizure prediction tech. Companies like NeuroVista, Biomedical, Epiminder.
Right, and the key insight here is that while it sounds amazing, truly reliable prediction in something as complex as the brain, it's incredibly difficult.
The trap is often high false positive rates, right?
Yeah.
Predicting seizures that don't happen.
Exactly, which can severely limit how useful and trustworthy the tech is in a clinical setting, even with advanced signal processing.
That's a crucial point. The gap between technically possible in a lab.
And reliably useful in the real world.
This connects to another source, too. A critical review on the diagnostic limits and potentials of EEG.
Yeah, it highlights where EEG is powerful, but also its inherent limits.
The insight being that EEG measures surface electrical activity. Understanding its limits means knowing what it can't see clearly.
Or where signals are too ambiguous to stand alone for diagnosis, it's not a crystal ball for everything in the brain.
And sometimes the limitations are more fundamental, like the medical device recall source, 2017 to 2024.
Looking at those trends, the common reasons for recall, it's a sobering reminder. Even highly regulated tech can have serious flaws.
Manufacturing issues, software bugs, usability errors.
It's the less glamorous side of medical engineering, but absolutely critical for patient safety. The insight is that the design, the manufacturing, just as vital and sometimes just as fragile as the science itself.
And then there are the profound human and ethical questions.
Definitely. The sources dive into ethical concerns of neural implants and the broader impact and ethics of AI-enhanced brain-computer interfaces.
This isn't just abstract philosophy, is it?
No, the insight here is concrete. As we get closer to directly reading from or writing to the brain, issues like cognitive privacy, they become very real.
Could your thoughts, your internal states, be accessed? What does consent even look like when the tech is evolving so fast?
How do we ensure equity when this advanced neural tech is likely expensive?
And what does interfacing tech directly with our minds mean for our sense of identity?
These sources lay out the specific challenges these technologies force us to confront now, not future hypotheticals.
Urgent questions.
Right. Even seemingly less invasive AI tools, like in scientific writing, ChatGPT author, get a critical look.
The insight isn't just, can AI write? It's about the challenge to academic rigor, authorship, bias, accuracy, reproducibility, when the writing process is kind of opaque.
It makes you question the foundations of scientific communication itself.
It's like every powerful new tool comes with this necessary, sometimes uncomfortable set of questions.
And these sources offer a toolbox for that critical analysis too, like image fraud detection.
Yeah, using techniques like error-level analysis to spot subtle changes in images, essential for verifying medical scans, for example.
And the data source dozen visualization. I love this one.
Oh, that one's brilliant.
It's a set of different data sets, right? All have nearly identical statistical summaries mean, median, standard deviation, correlation, all the same.
But when you plot them visually, totally different shapes, including a dinosaur.
The powerful, slightly dark insight there is. You absolutely cannot trust summary statistics alone. Visualization is non-negotiable.
The numbers can lie, or at least mislead profoundly. The plot doesn't.
It's a fantastic, fun, yet critical lesson packed into one visual.
We also touched on how engineering concepts pop up in surprising areas, like mental health, mental name.
Modeling psychological states not just descriptively, but as dynamic systems, using signal processing ideas.
And how tools like ChatGPT might bridge communication gaps, like a translator between technical engineering language and clinical terms.
And underpinning all this are the fundamental tools mentioned, PDF and feature extractors to get data out, ways to analyze EEG data quality.
Like impedance, cross-coherence, looking at synchrony between brain regions, insights into the raw data's cleanliness, its reliability.
And even simulators to generate synthetic biological signals.
Why generate fake data?
The insight is for testing algorithms robustly. Can your seizure detection algorithm find the pattern in noisy simulated data designed to mimic real-world messiness?
Synthetic data is critical for validating tools before they touch real patient info. Makes sense.
So, reflecting on this whole collection, what does this all mean for you, the listener?
You've seen how these sources offer this comprehensive, sometimes surprising window into biomedical data and tech.
We've gone from playful simulations teaching physics to sophisticated visualizers making complex biosignals tangible.
We've explored how our own perception can be simulated, even tricked.
And crucially, we've seen why approaching these powerful technologies needs a sharp, critical eye, constantly considering limits, potential failures.
And the deep ethical questions they raise alongside their incredible potential.
Yeah, this deep dive has really shown the diverse, sometimes unexpected ways people are building tools to explore and understand the human body and mind. Blending technical innovation with interactive learning and that necessary, sometimes uncomfortable critique.
So as you continue exploring this space, here's maybe a provocative thought to leave you with.
As these tools get more sophisticated, allowing us not just to understand, but increasingly simulate biology, predict conditions, even interface directly with the brain.
Where does that boundary lie between merely understanding our biology
And actively attempting to engineer or augment it.
and what fundamental, potentially uncomfortable, critical questions will that blurring line force us all to confront very soon?
Yeah, okay. That podcast is pretty good. So we need to make sure we actually download it and we add it to the page. It's an updated version. I will add the podcast on the top of the page. What?
Okay, so
I think there's a problem. Well, there's always a problem, isn't there? We love problems.
okay, so or generating patterns in that jazz. Okay, built with tools like 3.js, that 3D graphics library.
And the insight isn't just that they simulate it, it's how they let you visualize the electrical signals those implants send.
You can see the patterns, the timing,
Yeah.
crucial details.
Listen to an audio overview of Bionic Chaos, where we explore the intersection of biomedical data, technology, and education. This audio provides a brief introduction to our platform and the tools available for researchers, educators, and students in the field of biomedical engineering and neuroscience.
Yeah. Can you? Hey, can you remove the fluff and make it more conversational?
Made changes.
Discover how Bionic Chaos combines biomedical data, technology, and education. This audio gives a quick intro to our platform and tools for researchers, educators, and students in biomedical engineering and neuroscience.
Question: when we editing files, Is this any better?
It's how visualizing dynamic systems, it starts with these fundamentals.
Or the catapult animation, jumping cat. Simple illusions, like the Ponzo illusion, shows how our brain gets tricked by context when estimating size or distance.
Which is fun, but also kind of critical, isn't it? A reminder that our own biological sensors and brains, they aren't perfect measuring devices.
Not at all. We process, we interpret, sometimes with fascinating errors.
There's even a real-time speech visualizer.
Yeah.
Transcribes and shows audio characteristics as you speak.
And the one I found delightfully unexpected.
EEG music. Transforming brainwaves into music.
The ultimate biofeedback concert? Maybe. But what's interesting about EEG music isn't necessarily the artistic merit.
Right.
It's the insight into different ways of representing complex temporal data. Can we hear patterns we might not see?
An alternative way to explore brain states.
Exactly. These tools collectively emphasize that understanding biology means making its signal is powerful, but also its inherent limits.
The insight being that EEG measures surface.
The insight is that the design, the manufacturing, just as vital and sometimes just as fragile as the science itself.
And then there are the profound human and ethical questions.
Definitely. The sources dive into ethical concerns of neural implants and the broader impact and ethics of AI-enhanced brain-computer interfaces.
This isn't just abstract philosophy, is it?
No, the insight here is concrete. As we get closer to directly reading from or writing to the brain, issues like cognitive privacy, they become very real.
Could your thoughts, your internal states, be accessed? What does consent even look like when the tech is evolving so fast?
How do we ensure equity when this advanced neural tech is likely expensive?
And what does interfacing tech directly with our minds mean for our sense of identity?
These sources lay out the specific challenges these technologies force us to confront now, not future.
Like mental health, mental
Modeling psychological states not just descriptively, but as dynamic systems, using signal processing ideas.
and how tools like ChatGPT might bridge communication gaps, like a translator between technical engineering language and clinical terms.
And underpinning all this are the fundamental tools mentioned, PDF and feature extractors to get data out, ways to analyze EEG data quality,
Like impedance, cross-coherence, looking at synchrony between brain regions, insights into the raw data's cleanliness, its reliability.
and even simulators to generate synthetic biological signals.
Why generate fake data?
The insight is for testing algorithms robustly. Can your seizure detection algorithm find the pattern in noise?
Okay, so let's unpack this stack of sources you've shared with us. It's a really fascinating collection.
It is, yeah. Tools, simulations, articles, visualizations. It's mostly centered around biomedical data and technology.
Right, and our mission today is to really Okay, so
for everything.
audio characteristics as you speak.
And the one I found delightfully unexpected.
EEG music. Transforming brainwaves into music.
The ultimate
Critical, isn't it? A reminder that our own biological sensors and brains, they aren't perfect measuring devices.
Not at all. We process, we interpret, sometimes with fascinating errors.
There's even a real-time speech visualizer.
Yeah.
Transcribes and shows audio characteristics as you speak.
And the one I found delightfully unexpected.
EEG music. Transforming brainwaves into music.
The ultimate biofeedback concert? Maybe. But what's interesting about EEG music isn't necessarily the artistic merit.
Right.
It's the insight into different ways of representing complex temporal data. Can we hear patterns we might not see?
An alternative way to explore brain states.
Exactly. These tools collectively emphasize that understanding biology means making its signals and processes accessible. Sight, sound, interactivity, whatever works.
Okay, so we've seen the playful side and the powerful application of visualization for understanding biology. Now, here's where it gets really interesting and maybe leans into that critical, sometimes maybe even a little dark side.
Yeah, because while this tech is impressive, these sources also push us to think hard about limitations, pitfalls, ethical questions.
Absolutely. Take the forecast trap. This analysis looks at seizure prediction tech. Companies like NeuroVista, Biomedical, Epiminder.
Right, and the key insight here is that while it sounds amazing, truly reliable prediction in something as complex as the brain, it's incredibly difficult.
The trap is often high false positive rates, right?
Yeah.
Predicting seizures that don't happen.
Exactly, which can severely limit how useful and trustworthy the tech is in a clinical setting, even with advanced signal processing.
That's a crucial point. The gap between technically possible in a lab
And reliably useful in the real world.
This connects to another source, too, a critical review on the diagnostic limits and potentials of EEG.
Yeah, it highlights where EEG is powerful, but also its inherent limits.
The insight being that EEG measures surface electrical activity. Understanding its limits means knowing what it can't see clearly.
Or where signals are too ambiguous to stand alone for diagnosis, it's not a crystal ball for everything in the brain.
And sometimes the limitations are more fundamental, like the medical device recall source, 2017 to 2024.
Looking at those trends, the common reasons for recall, it's a sobering reminder. Even highly regulated tech can have serious flaws.
Manufacturing issues, software bugs, usability errors.
It's the less glamorous side of medical engineering, but absolutely critical for patient safety. The insight is that the design, the manufacturing, just as vital and sometimes just as fragile as the science itself.
And then there are the profound human and ethical questions.
Definitely. The sources dive into ethical concerns of neural implants and the broader impact and ethics of AI-enhanced brain-computer interfaces.
This isn't just abstract philosophy, is it?
No, the insight here is concrete. As we get closer to directly reading from or writing to the brain, issues like cognitive privacy, they become very real.
Could your thoughts, your internal states, be accessed? What does consent even look like when the tech is evolving so fast?
How do we ensure equity when this advanced neural tech is likely expensive?
And what does interfacing tech directly with our minds mean for our sense of identity?
These sources lay out the specific challenges these technologies force us to confront now, not future hypotheticals.
Urgent questions.
Right.
Okay, get the drill. We will update the front page, so it's more useful, and you'll have that audio podcast by Notebook LM. So check it out. Make sure it's available for you, and I'll see you next time. Bye. Okay, we're testing in production. Seem to work fine. Hope you like the colors. I hope you like the Notebook LM podcast.